What's up everybody, Phil here. Welcome back for part 5 of our tutorial series on building a neural network from scratch. To address a point in the last video, I had wondered about if I had made a mistake on the number of the dimensionality of this weight matrix, and I don't believe so, because if you take a look at it, looking at the end and output is the output, right? And so you don't want to add a bias unit to that because you're not connecting, because the output layer doesn't have a bias unit, and extending that logic to the other layers, the weight matrix doesn't have any input into the bias unit because the bias unit is just a constant. So this dimensionality is correct, and so we're free to move on with our neural network. So the next step is going to be to actually perform this feed forward. So we have our input data, we have the one-hot representation of our training labels, we have a starting point for our weights, and so now we can actually calculate an output for a single training example. And so we need to go ahead and implement this system of equations right here, the Z2, A2, Z3, A3, A4, and Z4, to actually get the output of our neural network model. So we'll start there, and then we'll add a function to calculate a prediction based on the output of the model. And following that, we'll go ahead and implement the function to calculate the gradient in parameter space. And then we'll have everything we need to go ahead and start learning with our model. So let's go ahead and get moving. We have our next function, as I just said, is going to be the feed forward function. And this is what is going to calculate the A's and the Z's of our model. In other words, we're going to calculate all of the units in the model here. So we need some input X and our weight matrices. And so we're going to start by adding a bias unit to the input, and the column within the row is just a byte of data, and so we need to add a column vector of ones. Let's go ahead and get some space. So we're going to start with adding a bias unit to our inputs, and that'll be our A1. So X is just our inputs, and we want to add it as a column. And now Z2 is just W1.A1. Right, W1 is a NumPy vector, and the NumPy objects have a method called dot that allows you to take dot products between vectors and matrices. And we want to actually transpose to make the dimensionality work out. And so I didn't do a slide on the dimensionality, but if you take a sheet of paper and consider the dimensionality of everything, meaning the inputs, the hidden layers and outputs, you'll see that we have to have this transpose here to get the dimensionality to work out in the inner product. And so I state that without proof, and we move forward by calculating the A2, which is just the sigmoid of the Z2. And now, since we transposed, we have to add bias units as a row. So the A2, then we're going to add the bias unit to A2, and we do this after doing the sigmoid because we don't want to take the sigmoid of the bias unit, right? We want the bias unit to be a constant, so we add the bias unit later. Z3 then is just going to be W2.A2. And we don't have to take the transpose here because we've already transposed. And then we can keep with the feeding forward the same way we did before by calculating the sigmoid and adding a bias unit to our second hidden layer, A3. And then we can calculate our Z4 as the product of our third weight matrix and our second hidden layer. And then the output is just sigmoid of Z4. And that is all of these equations here, right? So that is everything we need to do to feed forward our model. And then we're going to want to make use of all of this data later on in the program, so we need to return all of them. Return A1, Z2, A2, so on and so forth. So given some model, then we can actually make a prediction. So let's go ahead and define our predict function, and we'll just pass it the weights because we can make use of our feed forward function in here. So we can say A1, Z2, A2, Z3, A3, Z4, and A4 equals feed forward. And then our prediction, y predicted, equals mp dot argmax. We want to find the position of the output along with maximum probability along the column vector. Now, why is that the case? That's the case because the output layer, if you look at the math here, is a sigmoid function. So recall that it varies between 0 and 1. And so it'll be some continuous value, right? It's not discrete. It's not either 0 or 1. It is between 0 and 1. And that number is representative of the probability of the input sample being equal to that particular number. So you have a 0 through 9 10 element column vector with each row in the column having some number between 0 and 1 that represents its probability of it being that number. And the way we've arranged it is such that we want to find the position of that maximum number, the argmax, and return that as the most likely answer for the input data. And so we're almost there. So now our next function is to calculate the gradient in parameter space. And we're going to feed it a whole bunch of data. We're going to feed it essentially the entire model, as well as the output and the weights. So recall that we're going to do something called back propagation to calculate our errors. So I'm going to go ahead and leverage the awesome material from the Coursera class from Stanford taught by Andrew Ng on machine learning. You should definitely take this class. He gives a much clearer exposition on this topic than I can. But the basic concept is you start at the right side, the output of your model, calculate the error associated with that, and propagate it backwards through the model. And so he goes on and gives you a little idea of the intuition behind that. It's kind of complicated, but we're going to go ahead and just do it, right? So we're just going to get it done. So I chose this carefully so that we have the same number of input layers, one of course, one output layer, and 2 hidden layers, so we can just use a straightforward application of the algorithm he gives here. And so this delta 4 is the error in our output. So delta 4 is just the output of our model, A4, minus the actual training label, Y encode. Then we have to propagate backwards, getting Z3. Let me see, I think he has a better step-by-step example here. No, it must be up here. So let me find it right quick. Yeah. Well, whatever. So I thought I saw something that was a little bit more descriptive. Maybe it's something I wrote. But anyway, so our next step is to back propagate. So we want to add a bias unit to Z3 because we'll need that to calculate the next layer of error. So then delta 3 is just going to be W3, the weight matrix, transpose dotted into delta 4 times the sigmoid gradient of Z3. And this comes from here, right? We have W3 transpose times delta 4 times the G prime is just the gradient of Z3. And Z3 is an activation function, so we have to take into account the sigmoid gradient. That's what this G stands for, the derivative of the sigmoid function operated on the parameter Z3. And since we added the bias unit for dimensionality purposes, we don't actually want that, so we just discard that first row, right? Because we don't really care about the gradient of the bias unit. We completely discard that because it's just a constant. Z2, and we repeat the process with Z2. W2 transpose dot delta 3 times sigmoid gradient of Z2, and strip off that first row. And so then our gradients are just given by the A sub i's. So what we're calculating are the little deltas. These capital deltas are just the A sub I sub j's, A superscript L's subscript j's times the deltas. So the gradient itself is just given by this. And finally, bam. And the only thing we care about from this are the three gradients. Gradient 1, gradient 2, gradient 3. So I know this is a little bit unclear, and that's because I would really have to replicate all the material from the course, right? Andrew goes through great detail deriving all of this, and he does it very well. The purpose of this video isn't to teach you everything there is to know about a neural network, it's to teach you how to code one, just given some basic information. And so if you're the curious type who wants to know how all this is derived, go right ahead, take the class. It is well worth your time. And in fact, this is actually the hardest assignment in the whole class. So if you get stuck here, just press on and it gets much easier after that. So now we really are almost at the end. So the last thing to do is to actually run our model. And we have basically everything we need already in place. So we can just go ahead and get started. Let's do a save first in case something goes awry. So then I'm just going to call this run model, and we'll pass it some X input, a Y, and these are going to be for our training data, and then we're going to want to pass it testing data as well, because we're going to want to make predictions to do accuracy calculations. So one thing we haven't talked about is how you actually go about running these models, and there are a few things you need to know. So first of all, one common practice is to take all of your training data, your input data, and shuffle it. And you want to do that because sometimes there are patterns in the input data, right? You don't know how the MNIST data was stored, right? If they didn't randomize it, you could be training all of the zeros, all of the ones, then all of the twos, right? And that really isn't ideal. What you want to be doing is just training stuff so that in a random order, so that way you don't get kind of stuck in cycles, right? If you train a bunch of zeros, you're going to get trapped in one part of parameter space. Then if you try to train a bunch of ones, it's going to be further away in parameter space. So you want to avoid that problem altogether. So we're going to shuffle the data. And the other question is how many epochs do we want to do all this? So an epoch is really the definition of an epoch is some iteration on training. How many times do you want to train the model? So generally more is better. We're going to start with kind of a small number just to get some output onto the screen quickly so you can see what's going on. And the next thing you want to deal with is how do you want to chunk the data? So it's really slow if you were to try to run all 60,000 models, training samples at once. So typically what we'll do is we'll load up some batch, some very small number, and get feedback for that to allow you to iterate much more quickly. So that's kind of where we're going with this. So let's go ahead and proceed. So we're going to want to set up copies for shuffling, and we'll just do actual copies of the array. And we want to do a one-hot representation of our input data, and we're going to define 50 epochs. It's not very many. We'll just do that to get some data, and a batch size of 50. And so now we can go ahead and initialize our weights. And so if you look up at the definition of init weights, we have the number of features, number of hidden layers, and number of output units. So we have 784, right, 28 by 28 input features. We'll go ahead and make a 75 feature model. This is just kind of plucked out of thin air. This could be any number. And in a later video, we'll play around with it and see how that affects the output. But we're always going to have the 10 output units because we're classifying digits between 0 and 1. And so next up, we have to define our learning rate. And 001, 10 to the minus 3 is a typical value. This determines how large of a step we take in parameter space when we compute our gradients of our cost function with respect to the weights. And then we're going to want to anneal, as I said in the previous video, to some global minimum. And so we'll have some parameter eta that tells us how we do that. And we're going to want to decrease it every epoch by some number, and some small number, 10 to the minus 5, let's say. And we want to keep track of the previous gradients, and you'll see why in a minute. And we'll just go ahead and initialize that, like so. So next, we can actually start training our model. So for I in range of epochs, we want to keep track of our total cost because we're going to want to output that to see how the model is doing. And we want to shuffle our data at the beginning of each epoch. And all this is doing is shuffling. So now we have our shuffled arrays, and we're going to want to deal with mini batches because we don't want to train everything all at once. So we want to split that array along the 0th dimension along a batch. So for step and mini, now we're going to step through our mini batches and feed forward our model. A1, Z2, A2, Z3, A3, Z4, A4 equals feed forward X copy step and our weight arrays, and we'll be able to calculate a cost and pass it A4 as our model output. And to keep track of how we're doing, we want to go ahead and append that cost. And so we've fed forward our model. Now we can perform, let me go ahead and comment this, feed forward the model, and now we're ready to back propagate. So now we say we want our gradients, grade 1, 2, and 3 equals cop grad really hate that it doesn't tab it up correctly for me. That's annoying. Wow. So this is the Atom editor. I don't think it's really optimized for Python. So now these deltas come into play. And we want to use this eta function, this eta parameter. Oh, and it looks like I actually forgot. So at the beginning of each epoch, something I forgot is that eta function should be decreasing over time, right? So you want to decrease it by 1 plus the decrease constant, which I call dec, the decrease constant times I. So for every I, we want to decrease our eta. We want to anneal over time to the global minimum. So next, now we have our gradients and our deltas. We want to actually calculate the we want to actually update our weights. We want to do delta underscore W1 plus our learning rate times the previous step. Right, so for the first step, that's just 0, and for subsequent epochs, for subsequent steps, it's going to be a finite value. So now we want to update these previous values. Ha! I know I'm not supposed to go this far out. Kind of bad style, but whatever. So now we're ready to actually give some output. We want to know where we are in the epochs. It's always helpful to know if this thing is hung up. And after we're done, after the model is done learning, we can actually make some predictions. So we can take the test data, and pass in that, and then calculate some accuracy. We want to know where the training labels are equal to the predictions along the row axis, and we want to, oh, 1 second. Now that I have thoroughly ignored whoever was calling me, let's go ahead and proceed. So you want to divide that by the total number of training samples to get your percentage accuracy. And then we can kind of dump this out and see how our model is doing. And then let's return 1, just for grins. So now we are ready to actually run our model and see what we get. So we have our function up here to actually read the input data. I must have deleted the line, whatever. So train X, train Y, test X, test Y equals load data. And we're going to want to run model, feeding it the training data, training labels, test X, test Y. So now, moment of truth, let's see how many errors I've coded into this. Aha! So, invalid syntax on line 62. Of course, I'm sure there's going to be a bunch of these. We have an extra parenthesis. That's an easy one to fix. And I did the same thing down in line 82. NP. I actually want an extra parenthesis there. Make sure I didn't do that here, here, here. Okay. And then, oh boy. Okay. It's no attribute split line in the run model function in line 144. np.array.split. So, oh, it's array underscore split, not array dot split. Perfect. And so now our model is actually learning. It's going through the epochs. So what it's doing is it is shuffling our data at the beginning of every epoch and feeding forward the model and calculating gradients in parameter space. And so this will take a minute to run. The code isn't very optimized, so you can see it executes a little bit slowly. There are probably better implementations that are faster. And in fact, if you use a library like TensorFlow, it already does almost all of this for you, where you just basically input the data in some recognizable form, and you can load it up on your GPU to get ultra fast calculations. And so here we have a training accuracy of 91%. So 91% of the time, this naive, silly little neural network with only 2 hidden layers, only 75 units, actually produces a correct training accuracy. So that means that 91% of the time this model is right. And this took all of, I don't know, an hour to code up, a little bit more. And it's just a couple hundred lines about. And it's incredibly powerful and kind of interesting to me that something so simple can produce such an accurate output. And so I hope that was helpful. In the next video, we're going to look at playing with some of the parameters of the model to see how we can increase this 91%, and we'll also look at visualizing some of the test cases it gets wrong. So just to recap, what we did in this video was taking care of the feed forward of our model. In other words, implementing this system of equations for our model, and implementing a prediction function that tells you which one of those output units has the highest probability, We dealt with calculating the gradient of our cost function in parameter space. And we dealt with running the model. And so I would encourage you to go ahead and play around with more epochs, larger or smaller batch sizes, and see what you get with respect to the training accuracy. Turns out we're going to need to do some significant modifications to get, something on the order of 99%, which is a much better benchmark for the MNIST trading data set. But again, this is a very simple, naive implementation. I didn't do any optimization. No really significant thought went into it. It's just kind of, what's the simplest model you can come up with? And lo and behold, you get a 91% accuracy. It's actually quite good. So I thank you for your attention. Tune in for the next video. If you like the content, make sure to leave a thumbs up and subscribe for more. Thanks.